And let's welcome Paul Zmick, the Director of Energy Utilities, to give us a presentation on how to power UVA in a more sustainable way.
Thank you, Sophia. Can everybody hear me okay? Is my mic working? Great. Okay, good. First, I'm going to introduce myself, and then I'm going to start a PowerPoint, and I'll be speaking from the PowerPoint, and then I will take a dive into one of the final presentations of the Strategic Thermal Energy Study. So I am the Director of Energy and Utilities here at UVA. I've been at UVA 11 years. Before that, I was in private industry for 22 years, working for industrial companies like Coke and DuPont. I spent my 22 years across 5 different manufacturing plants across the southeast of the United States. I have an undergraduate degree in mechanical engineering from NC State, and I'm a registered professional engineer in Virginia, and I have a master's degree in systems engineering from UVA. And this is, I'd really like this to be an open conversation, so don't hesitate to unmic and ask me a question, unmute and ask me a question. And I'm going to start this presentation now. I'm going to share the presentation. Now I'll start the presentation, and I bet you I have to switch my screens, right? Yes? Okay. How about that? Is that better? Okay, great. All right, so thank you all for attending today and to learn about our Strategic Thermal Energy Study and how it relates to our decarbonization efforts at UVA. But in order to fully understand these, I'm going to share, I'm going to add the context of our existing energy diet and infrastructure. And then additionally, I'm going to share the bureaucracy of how studies and projects progress through UVA. And we are the definition of bureaucracy, which is a system of governance in which most of the important decisions are made by state officials rather than by elected representatives. So there is some bureaucracy here. And then establishing this context, once we establish this context, then we will explore some details of the Strategic Thermal Energy Study, which is specifically targeting our Scope 1 emissions, which is hence decarbonization. So you're going to hear probably many new terms and concepts today. So please stop me if you don't understand something. If I've said an acronym or if I said a word that you don't understand, just stop and ask me to explain that. It's very important that you thoroughly understand the systems, the energy systems in our infrastructure and our plan on this large and critical issue. Remind myself where the advance button is. So the outline of the entire presentation is, I'm going to give you some energy and infrastructure background. I'm going to talk about the capital planning process. We'll take a dive into the Strategic Thermal Energy Study, the process itself, and the high-level 5 elements and guiding principles, and then a detailed dive into the outcome of the Strategic Thermal Energy Study. So this was the first part of the presentation, which is the overview of energy and utilities, was a presentation I made almost a year ago. It was back in July of 2021 to the at the Strategic Thermal Energy Kickoff to help orient our consultants to energy and utilities at UVA. So I thought it was important that you hear that same information. So when I talk about district energy and district utilities, what the slide shows is the list of our utilities, our district utilities. So we provide steam for heating and building processes like sterilization and humidification and dining. They actually have cooking pots that use steam. And then we have hot water for heating buildings. We provide chilled water for cooling buildings. And we have additional utilities, which are really water-based, which are domestic water for drinking, showers, pools. The storm water, where does all the rain go, right? That's storm systems. And we have the sanitary that is associated with the domestic water. Once you use it, you got to get rid of it. And then we have power. Part of energy and utilities is we own and operate a 13,000 volt distribution, underground distribution system to all the buildings and exterior lighting. And the top three utilities on this are the thermal utilities. And those are the ones that are relevant to the strategic thermal energy study because they are associated with scope 1 and scope 2 emissions. And their district energy, the concept is you generate it at a central plant and distribute it to buildings. So you all probably have a good idea of how many buildings there are on grounds. There are about 550 buildings on grounds. And without district systems, instead of one plant or 2 or 3 plants, we would have 550 boilers and 550 chillers or air conditioners, and we'd have 500 different power panels, so or wires going to buildings, and those critical buildings would have to have redundancy, so we'd have a lot more than that. We probably have 700 boilers. So it's by doing district energy, you can consolidate all your production to large efficient plants, and then just have distribution to the buildings. And this covers about 18. We at UVA we have 18 million gross square feet of buildings. The majority of those are connected to district energy, over 12 million square feet. And that's a lot of space to heat and cool. So you're getting an idea of the size of the problem we have. This slide illustrates, first, UVA is a 1,682 acre urban campus adjacent to the small city of Charlottesville. And this is an image of UVA grounds, and the circles illustrate the 4 areas served by central plants. The largest one at the bottom, and hopefully you can see my cursor, is the heating is served from the main heat plant, which is on this picture, probably right in here somewhere. No, there's, yeah, we're right back here. There's another zone, which the plant is out of the parking lot. It's a building attached to the parking lot at JPJ. And so this is its own heating and cooling zone. The north grounds, which includes the Darden School, the law school, and JAG school, has its own small precinct utility plant, or PUP. And then our most recent PUP is the small plant that serves the new musculoskeletal building on Ivy Road. And so we call this the main heat plant, the Massey plant, the North Grounds mechanical plant, and the Ivy Mountain Cup. So I wanted to make sure folks understood the size of the problem and the complexity of the energy at UVA. So we have, I showed you before, the 4 central plants. Here's another way of looking at them. We have 9 chiller plants, which are the blue dots scattered across grounds. And we have 3 substations, the Cavalier substation, Alderman substation, and North Ground substation. And our diet of energy for heating is over 1 trillion BTUs. And so 1 trillion is 1 times 10 to the 12. So it's over 1 million BTUs, which is a lot of energy. And in case you don't understand what a BTU is, it's about a wooden matchstick. If you burn a wooden matchstick, that's about a BTU. Our substations, again, about a trillion BTUs of electricity. If you convert it, it's 300 million kilowatt hours. We have that electrical diet. And then the chiller plants, which is basically electricity, is about 1 trillion BTUs of electricity to make chilled water. So we have a huge energy diet at UVA. And so this is the majority of our, where our fossil fuels go here, is in that to heat buildings. And the utility side of it, this picture illustrates, is from our GIS system, and it shows the utilities. This shows the utilities across grounds, and it includes all our utilities. And we have 58 miles of thermal utilities, 146 miles of domestic and sanitary and stormwater, 43 miles of underground high voltage power, 6 miles of tunnels, and over 2,500 structures, which are vaults, these underground vaults that where we put valves and we put electrical connections, and we change directions in piping, things like that. And this is another illustration with just the thermal utilities. So, I'm sorry, this is just 31 miles of heating. So this is just steam, medium temperature hot water, low temperature hot water used to heat buildings. And this is, you can see this is energy data for 2020. I haven't updated this. This was, of course, from 2021, but what's circled in yellow there is the energy input for and I've highlighted the fossil fuel elements. And the plants represent about 85% of the total fossil fuel energy input at UVA. And again, these are in close to a million MMBTs. So this up through 2020, so it's 2015 through 2020, a 5-year trend of the same items highlighted on the last slide. So if I looked at that fossil fuel and I put the plants in the buildings, you know, from a plant perspective, what's really changed is we've been trying to minimize the use of coal with a target of 25% or less of the total heat input for the main heat plant for the year. And in 2020, we had an all-time low of 15% due to favorable weather and lower demand and coal availability issues. Right now, this year, we're going to probably be around that 15% again. You can see both are trending down. And if you add those together, you see the overall use of our fossil fuel is declining despite the strong building growth. So that's a good thing. The big demand from 2019 to 2020 is probably due to the vacancy associated with COVID and the favorable weather. I did want to talk about some current technologies that we are employing that you're going to hear throughout the strategic thermal energy study as well. So we're in the middle of a project that is converting, the image on the right there illustrates all the buildings affected by this conversion. So the main heat plant is here, and we're feeding steam and medium temperature hot water all the way up to the most distal points of our system. Would be Gooch Dillard here, Hereford here, and Kellogg here, and then way across at Carrs Hill up here and International Residential College.
Paul, we cannot see your clicker, but you're doing a great job of describing it. I just thought I'd let you know.
Oh, you can't. Oh, okay. You can't see my cursor. Okay.
But we're getting the idea, so keep it up.
Right. Thanks. And so this project now is converting those buildings from medium temperature hot water, which is over 220 degrees, 230 degrees typically. So it's high pressure water that would flash the steam if you opened it up, and steam to low temperature hot water. And why do we want to go to low temperature hot water? That's so we can use really innovative technology like heat recovery chillers. So by taking these buildings down to 160 degrees in the buildings and 170 degrees in distribution, we can use some cool and emerging technologies like heat recovery chillers that instead of, and what a heat recovery chiller does, it's like an air conditioning system, right? A chiller takes warm water and through a vapor compression cycle, refrigerant cycle, makes cold water, and typically it would eject that heat in cooling towers. Those are the cooling towers you see across ground. You see the big vapor clouds coming out when the water's condensing. And instead of rejecting it to cooling towers, we take that water and we recover heat. So we actually add a second compressor to the heat recovery chiller and make it even hotter discharge. And so we're able to take the water, the return water from grounds, the buildings, and heat it using the same piece of equipment that's making chilled water. So you have an efficiency of approaching 6, between 5 and 6. So for every 1 unit of energy in, you get 6 units of energy out. So this is an emerging technology that we've applied at 3 different places across grounds. And the heat recovery chiller we're putting in the north plant back here will be the base load, will provide the base load of heat. So it replaces 30,000 BTU hours of fossil fuel fired boilers out of our main heat plant. And finally, I just want to, this is where, this was the end of the first presentation I made to the Strategic Thermal Energy Study consultants. Our energy suppliers we get natural gas from the city of Charlottesville, and that comes from the Columbia Gas Transmission Line, which is formerly TECO, and we are interruptible service, which means we have no firm capacity for natural gas. And that's important. Remember that term, firm fuel, because it'll come up again. Coal, we get our current providers, Elm Street Resources, and we get it by rail car. Oil, we receive by tanker trucks from James River, primarily, or Tiger, and our electricity comes from Dominion Power. We generate very little electricity in grounds. Now I'm going to transition to the next part of the presentation, which is the processes. So at UVA, in order to perform a large study like this, this threshold kicks in that $300,000 to $500,000 range, or if you're doing a master plan, or if you're doing a study planning for a new building, you have to review the need with the Board of Visitors and get their support, get their approval. And once you do that, then you issue a RFP, request for proposals, and then you interview firms and you select a firm, an engineering firm or an architecture firm, and then you execute the study. And then the studies typically inform the capital budgets, and then you start the next process. But just the study part takes 1 to 2 years. And so once you have completed a study and you identify what capital needs you have, then you submit a capital needs request to the Board of Visitors. The Board of Visitors reviews it and provides approval and authority. So they approve the project and they give you a budget. They give you an authority to spend up to a certain amount, and then you're done. And then you do another RFP for a firm to do the design of the building or whatever it is you're building. In my case, it's energy plants. You go back to the BOV, they approve the firm you've selected, and then you do the design, bid, build process. And typically small projects you can do in a couple of years, big projects take 4 to 5 years. So that's the process. So I wanted you to understand the timeline. Like when someone says, why can't we get off coal? Because I have to do a study, and then I have to do a capital needs request, and that's a 3 to 5 year process. And then you have to do the phasing of the project. So it takes a long time. Now I'm transitioning to the strategic thermal energy study itself and the process. So the first thing we did was establish the guiding principles and stakeholder groups. And then the consulting team working with the energy utility folks had to understand the current energy infrastructure and technologies we are using that they could replicate, like the heat recovery chillers. We had to establish the current facilities footprint, which is that the current demand, the building demand. And then the consultants built digital twin models for buildings and projected the thermal and power demands by decade. So we looked at 2030, 2040, and 2050. What would this energy consumption look like in the future? And we had to do that so we could plan for the energy infrastructure. And then we looked at future strategies and constraints, like the limits on natural gas or electricity. And then we developed a high-level scenario for replacing fossil fuels. Once we had those high-level scenarios, we developed a rough order of magnitude for capital and operating costs for the implications of each scenario, so we could make decisions. And at this point, we haven't made decisions. We've just built a decision-making framework, or established some things to consider and look at. And then we also calculated what the carbon reduction would look like over time for each scenario, and how many RECs and offsets we need to meet our 2030 goal. And then the project recommended some short-term actions and capital projects, which we can review in a minute. So as the strategic thermal energy study was progressing, I realized there were really 5 elements. There were 5 elements of the study that were coalescing. First is to continue to drive building efficiency for new buildings and existing buildings. We have programs like Delta Force is a group that works on existing building efficiency, and they go do projects that improve the building efficiency and use the utility bills to pay back the cost of that. And we have facility design guidelines and green building standards that we're going to heighten. We're going to improve those, even make them more beneficial for energy reduction for new buildings. So we have to continue to do those things. And that was the first element. The next element is building and plant engagement. And so things like heat recovery chillers that are very efficient and use electricity as a fuel versus fossil fuels have a limited use because they work off of the combined, the coincident heating and cooling. So in order to drive the use of these new and emerging heat generating technologies that can displace fossil fuels, we might ask buildings to have a higher cooling load, an artificial cooling load, so that it can load up my heat recovery chiller to make heat. So it might be in the wintertime, we're actually using some of the exhaust air in buildings that have 100% outside air or have a lot of hoods, have a large air movement. I might drive some chilled water off in coils in those buildings in order to make my plants run more efficient. So that's a concept of building and plant engagement. So we're gonna right now, my plant only sees a pressure and a DP set point at the end of the line. It has no idea what's going on in the buildings. In the future, the buildings and the plants will work together to drive plant efficiency. Then there's plant infrastructure and improvement, and this is renewal. This is going into plants like the main heat plant where we have 6 boilers, in deciding what technology we're putting in there and what the phasing of that technology is. Like, first we get off coal, we move them all to natural gas and oil, and then we look at alternatives to natural gas, like renewable natural gas and biodiesel, or we look at other fuels that can utilize that existing infrastructure. But ultimately, way down the road, we're going to be looking at things like fusion or fission or heat recovery chillers or just electrode boilers to drive everything to a non-fossil fuel base. So that one element is that plant infrastructure over time. The other element that is a strong, it's a really positive outcome of the strategic thermal energy study was we took a deep dive into thermal storage, which is a seasonal thermal storage, which is really geo-exchange fields. So we looked across grounds, worked with the Office of the Architect, and identified all kinds of areas across grounds where we can install underneath things like athletic fields and underneath parking lots. We can put large geo-exchange fields that allow us to store that heat. So in the summertime, when we have excess heat from these heat recovery chillers, we can put it in the ground and store it there until we need it in the wintertime. In the wintertime, instead of discharging that chilled water up a building exhaust, we can take that chilled water and cool down our the geo-exchange fields, so that when we need that cooling in the summertime, we can pull it back out. So think of this seasonal storage as just following, chasing the season, sort of offsetting the heating and cooling need. So that's a critical element. And seasonal storage also shrinks the size of your plant. So by using the seasonal storage for peaking, it allows the plants to be smaller. So this infrastructure, the third element, plant infrastructure, instead of replacing in kind the size, we get to put smaller equipment in there, which takes less energy. And then the fifth element is offsets and RECs, understanding what type and quantity of offsets and RECs we need to meet our 2030 goal of being carbon neutral. And early on, we developed the guiding principles of the strategic thermal energy study. And you can see those. I'm not going to read through them. I'm going to pause here a little bit. And let you look at those. But number 5 was added in. I added that one in when we really started thinking about like full electrification. Electricity is not considered a firm fuel. So if we fully electrify and we lose electricity, I have to have a firm energy source and the availability to dispatch that in order to maintain heat in the buildings. So one of my single largest responsibilities is to always have utilities available for the university, and we have over 640 hospital beds. We have critical research and vivariums with animals. We have residential students that in the middle of winter, if we lose power, we have to keep heating these spaces. So the concept of a firm energy source was critical. And you can read the rest of it. So, and broad engagement with stakeholders in developing this plan is another one. So I'm going to pause here and ask for any questions. I'm going to stop sharing, and then I'll go into the PowerPoint. Oops. Let's see. Yes. Oh, 1 second. And Sophia, keep me. You need to probably give me a 5 minutes heads up on time.
Okay.
So what are you looking at now?
It's the strategic thermal energy study.
Okay,
Fine.
all right. So this was one of the reports, the most recent one to leadership. Okay, this is the leadership committee, and I'm going to go through this, and this is sort of the outcome and where we are in the strategic thermal energy study. So this was their agenda, and I'm going to work through this relatively quickly. Okay. But this is everything I've talked about there. That's sort of the process. So there's sort of 3 scenarios that we've identified, and then how those scenarios imply what's going on in the buildings and the central utility infrastructure. So scenario 1 is right now we're in the process of converting everything but the hospital, the medical center, off steam. So scenario 1 says the medical center stays on steam, and we move from fossil fuel based steam production to some other technology that can produce steam with renewable energy. And that could be renewable electricity, or it could be renewable natural gas or something like that. And so From a building perspective, you can see the existing buildings where that modify airside economizer operation to maximize, that's that building engagement. So we do that everywhere. Consider driving airflow setbacks to further reduce energy consumption without compromising operations. And this is particularly important in like the hospital, where they have a lot of air turnovers, which takes a lot of like energy. And so we really want to take a look at minimizing that. So on the new buildings and major renovations, an important aspect, I'm going to point out decoupling low heating and cooling from the HVAC system. So when you think about old radiators, they provided the heat, but it wasn't through your air conditioning system. So you're able to move a lot less air if you have just enough air for ventilation requirements, for fresh air requirements, and your heating is cooling is done by passive aspects of your buildings like chilled beams or radiant heat panels and floors. So that technology allows us to really minimize the amount of air we're pushing around and reduce energy consumption. And what happens to the central utility infrastructure? We minimize that steam system and the equipment required to just what's required for the medical center. We eliminate coal, and we start using things like renewable natural gas to reach our 2030 goal and beyond that. And then some future technology, we electrify, but we don't understand what that technology is right now. We continue to use heat recovery chillers, and then with geo-exchange. And those are across all the scenarios. And then scenario 2 is just total steam phase out, which is probably a $100 million project to convert the hospital at least off steam with some significant issues. And the big one is sterilization. That's the big issue that the medical center said we really need to see a solution on that before we'll even consider getting off steam. And then this scenario 2 has total steam phase out plus some things like renewable natural gas or other combustion. And then scenario 3 has total electrification. So it really eliminates all the combustion by 2050. And we are somehow, with some future technology, totally electrified.
Oh, look, come here.
They talked about some proven technologies. Isn't it the concept of the overlapping heating and cooling with heat recovery chillers? And we're implementing that now. We will implement, hopefully, geo-exchange. And then the future technologies, small modular nuclear reactors, that is an up and coming technology that EPRI's continued to develop. And I was at a conference a couple weeks ago where I think it's Cambridge Fusion Corporation believes they will have a tokamak fusion reactor by 2025. They've developed a magnet 20 times more powerful than the current magnets on the market. And they believe they will have a sustained fusion reaction that produces heat by 2025 and a sustained fusion reaction that produces electricity by 2030. So those are those future technologies that we're going to have to keep an eye on. So it might be that technologies like that are allowed to plug into the grid and provide a stable electric grid so we can migrate to an all-electric solution and not have to worry about grid instability, or even put something in the plant here on grounds that generates our heating need without combustion.
Paul, there are a lot of like new big ideas to me on these couple slides. I don't know if there's an interest for others to dive in more. One that you've mentioned a couple times now that I'm not actually familiar with is the concept of renewable natural gas. And I saw that there's a chart for that. I don't know if we want to go into.
Yeah, so renewable natural gas, and there more and more projects are being developed, and this is where they could take a dairy farm, and there's one in I'm forgetting, it's down in Virginia, I'll think of it in a minute, where they have a collection of dairy farms. The Dominion Energy is taking those dairy farms, and on dairy farms in particular, they take the cow waste and they put it in big pools, right? They put it in big waste pools. And if they cover the waste pools and collect the methane, then they can filter the methane, compress it, and inject it into the natural gas pipeline. So it's a green molecule that has, maybe 80 times the impact, right? Because 30 or 50 times, whatever it is, the equivalent CO2, right? It's a more significant removing methane than CO2 by a factor of 30 to 50 or whatever your factor is. So they take that and inject it into the pipeline. And if they were Waverly, down in Waverly, Virginia, so if they were to do that in Waverly, that pipeline is connected to the one that we take our natural gas from. So it'd really be by displacement. So that's an offset. That is not stopping fossil fuel combustion here, but it is someone else is getting the beneficial use of that renewable natural gas, right? So somebody's burning natural gas, those green methane. Now, these projects are popping up all over. Swine farms, dairy production, poultry processing, and vegetable processing. They all have these large waste streams, these industrial waste streams that they can compost, collect the methane, and displace mineral gas. And they're just popping up all over across the United States. But there's probably not enough of it to satisfy the entire, I know there's not enough, the natural gas diet. So that's I think a short-term solution.
That's great.
And then this one, it says raw water heat recovery. So this is a picture of the, I'll stop. Does somebody have a question?
No, I was just going to say 5 minutes warning.
Okay. This is a picture of the water treatment plant up at OHEL above Kellogg Dorm would be right at, well, you can't see my cursor, would be right where that water thermal energy storage tank is Kellogg Dorm. And they bring water, this is operated by RWSA, our local water authority. They bring water from the reservoir, what's the reservoir out?
Ravenna.
Yeah, but it's the one, I can't think of the name of it now.
Ragged Mountain?
Yes, Ragged Mountain Reservoir. So they bring raw water from Ragged Mountain to this site, and they take and they filter it and they treat it with charcoal, like they filter it with charcoal, and they add chlorine to it, and then they send it out for us to drink. But that raw water has energy in it, has a lot of energy. And so one of the concepts I introduced during the study is, can we reduce their water temperature by 5 or 10 degrees and take that heat and put it into UVA? And they said, absolutely, cold water is better for our processing. So we're working with RWSA and to maybe install, they need to put a new 36-inch line from this plant to the reservoir. I might put in 2 10 or 20-inch lines in that construction. So I either have access to the reservoir heat source and sink, or just the water that they process at the plant. But that's a way we could recover a ton of heat out of a resource that's in our backyard, and displace some of the fossil fuels. So we're looking at technologies like that. And I'm going to go, so this is the executive summary. So they did, the growth projection said we're going to increase building space by 33% by 2050. We're going to take out the high energy buildings, the older ones, and the scenario 1 has still high source energy requirements because of the combustion, low efficiency combustion. And scenarios 2s and 3s, the conversion to hot water is much better. And scenario 3, we really reduce the energy input because we're using the high efficiency heat pumps. Now this chart is misleading. So their estimates were high, but it is going to be expensive. This is going to be, this is probably going to be a $500 million effort to get off fossil fuels. They included a bunch of costs on electrical infrastructure, which I don't think we need. We've come up with an innovative way to really use what we have. We'll need very little electrical expansion. And this is just the building growth by zone. So they took it by zone and by type. And then they built this digital model and showed that if we have a 30% reduction in EUI energy use index, that, you know, we implement these new building improvement guiding principles, we can really reduce our energy footprint. And these are the peak load projections for heating, cooling, and power. And it's not much of an increase considering 33% increase in building load. The cooling load goes up because we're going to use things like the building engagement to actually increase our cooling in the wintertime so that we can run our efficient heat recovery chillers in the wintertime to make heat. This is just expansion cost by district, by area. And this is existing substation load and future substation load. So we went through and understood where the growth is going to be. And this is the economics they used. These are the elements of that. So one of the things we had to do in the strategic thermal energy study was get some idea of what the cost of fuel were going to be and alternatives. And this chart illustrates, you know, the current natural gas and firm natural gas are going to stay pretty flat, they project. And then RNG is where it is now and where it's going to go. And then biodiesel is an expensive fuel, but we would only use that for an emergency. Biodiesel would be our firm fuel backup. So that's where I would have that, is stored across grounds where I could use it either to run a generator to create electricity, or to combust it in some of the old combustion assets to make heat. And then the electricity projections, these are the two big offshore projects that Dominion is putting in. Those two big spikes in rates, they're going to have to recover those costs. And then when they do, they should go down over time due to the efficiency of the phase out of fossil fuel-based assets and the increase in renewables. So these show the different elements of the heating production for the different scenarios. Again, scenario 1 and 2 had a higher heat input because of we're still doing combustion. In scenario 3, the all electric solution includes, and this pink says electric boiler, but it could be some other electric asset. And you can see the heat recovery chillers, a known technology, which is continuing to improve, plays a big element in where our fuel comes from. And then this is geo-exchange, and then daily thermal energy storage. So we increase sort of the daily thermal energy storage, and this is seasonal thermal energy storage. This was striking to me that, you know, this third scenario really reduces our heat input, which is where we want to be. Again, this is longitudinally for each scenario. So over time, how those energy inputs transition and what that implies. And then this is the capital cost of the scenarios. Maintaining our combustion assets is less capital cost intensive. But this, and you can see the big yellow bar at the bottom was the electrical infrastructure. They have $295 million, $291 million allocated for that. I think that we can do that for probably half or less. So I would say that number should be more like 150 million, and the rest of those are probably pretty accurate. That seemed to be the one that they missed on. So we're talking, you know, I would say half a billion to $700 million, $500 to $700 million cost over 30 years. And the first thing we're going to do, the first project I'd like to kick off is this conversion of 2 of our 3 coal boilers to gas and biodiesel. And hopefully we can get that done in the next 3 to 5 years. And it does, because those fuel charts you saw, the increasing fuel costs, our cost to operate does go up significantly. But this again is the projections of fuel costs are really not that credible at this point. I mean, we really don't know where the cost of electricity and fuel are going to be. But if you use those projections they use, this is what it would look like to service the debt and then the operating cost of the plant. So still scenario 3, it costs more, so you have more debt, but your operating costs are very close to what they were today. And then these are just the numbers they used for their greenhouse gas projections. And these are the scope 1 emissions, and this is for, scenario 3, it should be 0, it is here. So these are the different scenarios and the different emissions, what they're going to do over the decades. So the next step, we're going to look at things like the risks associated with some of these scenarios. And we're going to review prioritization and look at things. Can we have curtailment plans, again, to minimize the infrastructure needed? And how do we do that? And then we're going to look at the reliability, this firm fuel concept, and what we do to things like diesel generators and all the other little sources of fossil fuel on grounds. And so finally, what they recommended is we continue to work on demonstrating some engageable loads between buildings and plants. We look for alternatives for steam for the clinical applications like sterile processing. We demonstrate an adiabatic humidification, which is just a different way to humidify and not use steam. We work on airflow setbacks in both buildings and laboratories. And there's a great program on that already that the sustainability folks can talk about. But the big one is to explore geo-exchange, take a deep dive into that, do some test wells, and really understand what the geo-exchange potential is. And then the first thing he said is, gosh, it's a no-brainer, get off coal, right? That's a big hit. I'm going to stop sharing there, see if folks have any questions. I do have one more slide that, if you want to talk about geothermal, we'll come back to it. But we were very lucky at UVA, and that we have a graphite deposit underground, it appears. And graphite is like the silver bullet of geo-exchange. So we might be able to install, reduce the cost of geo-exchange because we have these super high performing wells. I have one little chart that helps illustrate that. But I'm going to pause now for questions or let Sophia take back over the meeting.
Great, thank you, Paul, for a very informative presentation. I think we can now go into breakout rooms. I think 2 breakout rooms will be fine. And I will open the rooms now, and each will have like about 20 minutes to discuss.